Okay, last video on Anova, and this is our walkthrough an SPSS example of Anova. For this example, I've pulled some data from the CDC. So this is real live data. It's a large-scale data set, and I encourage you as you go through your program, start investigating some of these large-scale data sets. So this is publicly available. It has many questions over several years, and so you could, or a person could certainly develop a dissertation based on some of this publicly available data. And a lot of times the publicly available data will sufficiently capture whatever that investigation is that you want to pursue. So anyway, just something to think about. For this Anova example, we're going to look at grade level, and I want to come over here to variable view so I can get kind of the coding of that, because I want to know, I know it doesn't mean fourth grade, so let me look at the label and just pull it out here a little bit and see. They just abbreviated on the label. So on the values, I could see that the ones are 9th grade all the way up through 4 being 12th grade. So they're looking at 9th through 12th graders. And they're asking them all sorts of questions. The variable I'm interested in is this body mass index, or BMI. So maybe I was some sort of health educator or just had an interest in this area, and I want to know how does the body mass index compare 9th through 12th grade for the students they've included. If you scroll through the data and scroll through the labels, you can kind of get an idea of what types of questions they're asking, like drinking and driving, texting and driving, carrying a weapon at school, carrying a gun in the past 12 months, physical fighting, forced sexual intercourse, sexual violence, dating violence, and so on. And it's just incredible the number of questions that are addressed here. So it's a really interesting data set that I just pulled it from the CDC. And in fact, if you go to the CDC, they have many data sets. So this is not their only one. They have lots of large scale surveys going on to kind of keep track of what's going on in our country. So, but out of all these variables, we're going to isolate a couple of them, and we're going to look again at grade compared to BMI, and BMI is over this way. Oh, there it is right there. So we have some missing information, but that's not a big deal. So we're going to run a one-way Anova and make this comparison. So just like before, we're going to go to Analyze, Compare Means, and then there is one-way Anova right there. All right, and I've clicked over the variables we care about. So our dependent variable, or our outcome variable, is that BMI, that body mass index. My factor, that's my grouping variable. So I pulled over that grade variable. All right, look, here's the post hoc button I was talking about earlier. If I click on it, you could see I have quite a few to choose from, but I'm going to select that kind of general middle of the road post hoc, the Tukey test. And then under options, I want to ask it for descriptive statistics, because that's interesting to me. I want to take a look at those means for each group. And then I also want to look at the plot of the means. And the plot is, a lot of times it's just interesting to look at. It's a visual representation of what our numbers are going to tell us. All right, then I'm going to say OK. And here are my findings. So 9, 10, 11, 12, you can see I have 34,000, 34,000, 33,000, 34,000 participants in each grade. So it's quite a humongous sample, right? So 137,285 total participants. You can see the mean BMI values for each of the 4 grade levels. and you can see the standard deviations. So not a lot of variations between the standard deviations. They stay pretty consistent. You can see the minimum and maximum. So you had some BMIs of 0, yikes, and a BMI of 219. Is that possible? I guess it is. That's interesting. But let's go ahead and look at our Anova results. So remember, here sum of squares is an indication of your variability. So we want to know, how does the variability between our groups compare to the variability within our groups? And then we're going to take a look at the variability, the total variability, here in a minute. But I can see my degrees of freedom. So I have 3, because remember it's k minus 1, or number of groups minus 1, which would be 3. And then the within groups would be the number of participants minus the number of groups, right? So here are my total participants, 137, 285. You can see that that's 137, 281. So that is this minus the number of groups, which would be that, right? And then putting it back together, you have your total. Mean square and your F value. Holy cow, that is a huge F value. Right, 536. So think back to the little things we were drawing, where we had 0, 1, 2, 3, 0, -1, -2, -3. So imagine in your head where 536 would be. It would be way out into the tail. Again, the tail never touches the axis, so we're never going to get to quite 0, but it's going to be pretty close, right? So it's definitely a significance value of 0.000. All right. So if I come back over here to my document and make some notes based on the null hypothesis and so on, like we've been doing. Let me get that ready to go. Okay, so like before, we know how to state our null. So we have our null hypothesis is the mean of 1 and the mean of 2 and the mean of 3 and the mean of 4 is going to be 0. So there are no differences. And then the alternative would be, I'm just going to use little quotation marks, would be all of this is not 0. We're saying, yeah, there are differences, right? Okay. Well, kind of going with our idea of being able to move a little faster now that we're getting the hang of it, I know that p-value was 0.000. I also know that my, oops, that's not right. I also know that my alpha is 0.05, right? Just like it's been all along. So if I'm making that comparison, and I have 0.05, and I have my little circle like in first grade, I know that this is less than 0.05. If it's less than 0.05, if 0.05 is here, then it's going to be further out in the tail. So that probability is going to be less than my cutoff value, my critical value. So it is going to be what? Statistically significant. All right. So I would do the same thing I've been doing before, like findings, blah, blah, blah. We do have statistical significance, and same thing as before, but now it's going to be F, right? And we're going to have 2 degrees of freedom. That's going to be a little comma. I'm going to click back over here to the output, because I need to pull those degrees of freedom. I know the first one's going to be 3, and the second one is going to be my total value, so 137, 284. All right, so this is going to be 3, 137, 284 equals, let me scroll down a little bit, equals that giant F value. Remember what it was? I don't. It was 530, let's just say 537. Let's round up. 537 equals 5 37, and then P equals 0.000, right? So we did find statistical significance. We could have looked at that humongous F value and known that it was going to be way, 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 way out in this tail, probably statistically significant. And then when we looked at our P value, we said, yep, definitely statistically significant. And so these are the numbers we would pull to determine that. But this is a good example of, let me look at that output. This is a good example of how sample size can influence statistical significance, because this is a massive sample size. But let's look at these means. I mean, really, 22, 23, 23, 24. So although it is picking up as statistically significant, these means really aren't that different, right? Can you see that? The differences in the means are not much. So if you kind of reach back to where we were looking at the formulas for the z-test or the t-test, our denominator, our n, is so big that we're getting almost an artificial result here, right? So it's saying that your means are different, even though they're just a tiny bit different, it is statistically significant. But it's, I don't want to say it's misleading, but it's a little bit inflated or a victim of sample size, right? So the sample size is causing it to be statistically significant. So what we want to do, especially, well, in all cases, but especially in cases where we know our sample size is huge, is we want to calculate our effect size. Because here we know, oh yeah, statistically significant. But what about that practical significance? Is it useful? Is this a meaningful difference, right? Is it practically meaningful? The effect size for Anova, like I mentioned briefly, is called eta squared. And the way eta squared is calculated is through looking at the variability. So what we're going to do is take our variability between groups and divide it by the total variability. That's going to give us an indication of shared variance. You know, how much shared variance do we have? Or what is the impact of grade level on BMI in a more practical sense, okay? So let me come back over here where I can write. Okay, so just to remind you, the effect size is eta squared, or you can use the symbol eta squared, is equal to the sum of squares between and the sum of squares total. All right, so that, like I said, comes from your SPSS output. So for this, if we have eta squared here, or you can use the symbol, it's 40,557.4 divided by 349,671.4. That's going to give us our effect size. So I'm just going to grab my calculator. I didn't do this ahead of time. So 40,557.4 divided by 349,671.4 equals a decimal. So let me write the decimal here. It equals 0.00116034. It's a long decimal. Okay. In this case, you certainly don't need all those decimals. So what if we shorten it to 00, how about 12? We'll round up here. Okay, so we're going to shorten it to 0.0012. This is in a squared metric. Look how it's eta squared, and we had sum of squares. When it's in a squared metric like this, we can talk in terms of percentages, right? So this 0.0012, if we move that decimal over a couple of places, this becomes 0.12%. All right. So again, this kind of highlights the problem with statistical significance testing, because if I only looked at this finding right here and I saw that my probability was 0, so what it's saying is, would I have gotten the mean values I got if the null is true is really, really tiny. Therefore, the null is probably not true. I'm going to reject that null. So statistically significant, yes. Practical significance. So this finding means, I was trying to get a clean sheet here. Where's my cursor? I'll just write small. What this means is, in practical terms, I do not have it together. Okay. It means that 0.12% of BMI can be explained by grade. All right. So that's not very much, is it? So 0.12% of that BMI can be explained by grade. All right. If you're more of a kind of a Venn diagram type person, if you think of grade being here, BMI is just barely touching the grade. There's just almost no overlap right here. So this is BMI and this is G for grade. So there's just about nothing going on here, really, in a practical sense. Even though, look at that, we found statistical significance. When we look at the practical significance, there's just not much of a relationship here. Which, when we kind of glanced at our means, we could tell there's really not that much of a difference between and among our grade levels, even though we found statistical significance, right? Okay, so I hope that makes sense to you. Even though the effect size, the practical significance, was pretty tiny, the 0.12%, let me go ahead and touch on post hoc tests. Because again, this information just tells us, oh yeah, your groups are performing differently. But it doesn't really tell us which group is scoring differently from which other group. Now, I can look at the means and get an idea of what's going on, but are any of these groups statistically significantly different from another group? All right, and that's what our post hoc test is going to tell us. What this table is used for is to make those pairwise comparisons. So it's looking at 9th grade compared to 10th grade, and then you scroll over here. Now look at all that. It's all statistically significant, but we know that's probably because of the large sample size. But anyway, we're going to go on and look at it. This is saying that 9th grade is performing statistically significantly different from 10th, and then it compares 9th to 11th. Get rid of that thing. 9th to 11th, and then 9th to 12th. So it's saying that 9th grade is performing differently from all the other grade levels. And I know that because it has a statistically significantly different result over here. When 10th grade is compared to all, now this is a repeat, right? Because we've already looked at 10th grade compared to 9th grade. So some of this table is repeated information. We've already looked at that one, but now 10th grade compared to 11th and 10th grade compared to 12th, again, not surprisingly, statistically significantly different. 9 to 11, now we've already looked at that, right? 11 to 10, we've already looked at that one, but here's a new one, 11 compared to 12th grade. Yep, that is statistically significantly different as well. Okay, so now I think this is all repeated, isn't it? This is all a repeat down here. But in a situation where you don't have such a massive sample size, these will not all be statistically significant. It's just a function of our sample size again. But in other cases, this would be a more interesting table because it would really break down and talk to you about which groups are performing differently from which other groups. All right. And the same thing with your homogeneous subsets. In a different situation, this is going to give you an idea of, are any of your groups kind of performing similarly? Like if 9th and 10th grade had a more similar result than 11th and 12th grade, you'd have 9th and 10th kind of together here, and then 11 and 12 by themselves, and so on. So I encourage you to look at this and another example other than this one. I picked this one, even though these results are what they are. I chose it because it is real data, and I like, whenever possible, I like for you guys to see real data. The mean plot is, again, just a visual of what we've seen. Now, visually, it looks like BMI is going up over the years, but we've got to keep our scale in mind, right? So it goes from higher than 22.5 up to less than 24.5. So there's, as far as percentages go, there's not much there. It is kind of encouraging to see, though, because those are pretty good BMIs, especially if you're considering boys and girls together. What's the BMI level when you start being obese or overweight? Is it like 26% or something like that? So it looks like 9th through 12th graders, at least 100,000 plus, as part of this survey, are doing pretty well as far as BMI goes. But anyway, that is off topic of the Anova. So that is an SPSS example of Anova. I encourage you to run it on your own. I'll drop this data set into the file that corresponds to this lesson. And that wraps up the analyses for this course 8307.